extraneous roots occur when you are solving exponential equations sometimes. And typically these happen when you have to use a quadratic formula or you're solving a quadratic form of an exponential equation. And you'll see what I mean in a few minutes. So some algebraic methods of solving exponential equations can lead to extraneous roots. And these extraneous roots are solutions that are not valid to the original equation. And so typically what ends up happening is you might get a solution like 3 to exponent x equals negative root 3. Okay? And what happens here is, because you're looking at a power, you know that a power has to be greater than 0 always. And so that's why this solution here would not make any sense. And if you actually look at this in a little bit more detail and you try to solve for x, what you would be doing is finding the log of both sides to get the x down. And what you'll notice is, what you try to do on the right hand side is try to find the logarithm of a negative number. And you know that a log of a negative number does not exist. We know that logarithms only exist when you're looking at values that are greater than 0. So just to remind you why that happens as well, if you think about the graph of a logarithmic function, all the values of the logarithm have to be positive numbers only. Okay? So that's why solutions like these don't exist. And sometimes when you're solving exponential equations, you do get an extraneous root, a root that does not make any sense and is not valid to the original equation. So here's another example. So let's say you're solving an exponential equation and you get a solution like 2 to the exponent x equals 1 plus or minus the square root of 5. Now what that means is I have two solutions here. I have 1 plus the square root of 5 and I have 1 minus the square root of 5. Now the first solution, if I ignore the other solution that's here, if I look at the first solution only, to solve for x, I would take the logarithm of both sides. Then I would use the power law to bring down the exponent, which is x. That's what I'm looking for. And then I would divide both sides by the log of 2 so I can get the solution for the logarithm. And so I get an exact value of log of 1 plus the square root of 5 divided by the log of 2. And then I get an approximate value of x equal to about 2.08. And if I apply that exponent in the original problem here, it makes sense. Okay? If I look at the other solution, where it's 2x equals 1 minus the square root of 5, what you'll notice is that 1 minus the square root of 5 is a negative value. So if I do that on the calculator, I get 1 minus the square root of 5, which is negative 1.2. Now if I try to find the logarithm of both sides in this case, I know that on the right hand side I cannot find the log of a negative number. And so we also know that a power must always be a positive number. And so what ends up happening is you get an extraneous root. So this answer here does not make any sense based on the original problem. And the original problem is that you're solving an exponential function. And you can't have a negative result when you're looking at an exponential function. So let's take a look at one example. And this example may or may not have an extraneous root. It depends on what kind of problem you're looking at. So not all exponential equations will have an extraneous root. Sometimes they will, sometimes they won't. So here's the first example we're going to look at, and it says solve each equation. And you'll notice that on the left-hand side, we actually have two terms. So I can't just easily find the log of both sides and work with it from there. And when I say it has two terms on the left-hand side, I mean it has two exponential terms. Okay? So when that happens, I can't actually find the log of both sides, so I have to use a new method. So one thing to think about is, if I'm looking at the left-hand side here, can I factor out the left-hand side? And if I can factor it out, that'll make my work a lot easier. So let's take a look at what 2 to the exponent x plus 2 and 2 to the exponent x may have in common. Now I can rewrite 2 to the exponent x plus 2, and if you think back to the warm-up, we had a question where we were looking at 2 to the exponent x multiplied by 2 to the exponent 2. And we knew that using the multiplication rule in with exponential powers, we know that if you have the same base, you can add the exponent. So that's the same as 2 to the exponent x plus 2. And so because these two are equivalent, I can actually go backwards and rewrite 2 to the exponent x plus 2 as 2 to the exponent x multiplied with 2 to the exponent 2. Okay, so there's another way of writing the same thing. And then I have minus 2x equals 24. Now if I look at the left-hand side again, what you'll notice is both of the terms that are exponential have a common factor of 2 to the exponent x. So I can actually factor that out, and we actually did this in the warm-up as well. Okay, so I'm going to factor out 2 to the exponent x, and I get 2 to the exponent 2 that results from the first term, and 2 to the exponent x divided by 2 to the exponent x gives me 1, so minus 1, and that'll equal 24. And if I simplify what I have inside the brackets, I get 2 squared minus 1, which is 3, equals 24. And now I have multiplication between an exponential part and just a regular number. And so I can actually take both sides here. And the opposite of multiplication is division. So I can divide both sides by 3. And I get 2 to the exponent x equals 8. Now, here's an exponential equation that I can actually solve. I can rewrite 8 with the base of 2. And so I would get 2 to the exponent x equals 2 to the exponent 3. And since the bases are the same, therefore I know x has to equal 3. So there's one example of solving an exponential function where one side of the equation has more than one term. This case, we did not have an extraneous root. Now I can check my work quickly by looking at the left side. And you don't have to do this every time, but this is just a quick little way of checking to see whether or not your work is correct. And if I plug in the exponent or the value of x that I got, I have 2 to the exponent 5 minus 2 to the exponent 3. That's 32 minus 8, which is equal to 24, and that's what I have on the right-hand side. So most likely I did my question or the work correctly. Okay, just a quick way of checking your work.